Okay. Um, so, in today's class we will be discussing about the wind heeling arms and how do we calculate the stability of a ship subjected to wind heeling. First of all, as I told you before, suppose you have a ship like this and there is a region of it below water, there is a region of it above water, this is the draft and this is the freeboard. So, that much distance you have. Now, on this freeboard the wind acts and the wind acts on the surface, and the way in which I will tell you, there is a uniform pressure offered by wind on the, of course, it might not be uniform, but in general over that area we consider a uniform pressure is offered by the wind. This pressure acts on that area that is exposed to the wind, which is called as the windage area or as the sail area, two things. It is called windage area or sail area. Okay. So, these two so this is subjected to that area, and therefore, that pressure into that area is a force that will be acting on the on one side of the ship. Now, this force is acting, we can assume it to act at the center of gravity of the windage area. Means if this is the ship, means if this is a ship, if this much is above, this is above water, the freeboard. So, half of that freeboard, at that point we can assume the center of gravity of the windage area to be located at, and there the you can assume the wind force to act at that point. And when this wind force acts, there is a tendency obviously for the ship to move like this, displace horizontally like this, but this is prevented from happening by the water. The water resists the movement of the ship. Actually, air also resists, but air the effect is very less because its density is much lesser, but water has a very strong resistance and therefore, it prevents the ship from moving like this. Now, our calculations, we are assuming that the ship does not move at all in this direction, in the transverse direction, the ship does not move at all. Therefore, the wind force is balanced by the reaction force from the water. So, there is a reaction force acting here. Now, this reaction force is also a it is also a pressure that acts over the entire area. So, we can assume that to be a constant force acting at the centroid of that area which is under the water. The centroid of that area under the water will be T by 2, T is the draft. So, T by 2 will be the centroid of that area or the centroid of that portion. So, at that point at T by 2 you will have the force from the water, reaction force from the water, and at so from that point plus T by 2 will give you the surface, plus an L will give you the distance to the centroid of the windage area. So, that L plus T by 2 will give you the distance between the centroid of the windage area and the centroid of the water, centroid of the region below the water. Okay. So, it will be like this if you draw it. So, this region, this is what I am saying, this is the windage area. So, at the exact center of it, we will call this distance L, then at the exact center of this will be T by 2, T by 2, T by 2 and L. So, the distance between the so, this book uses not L, it uses HV, they are calling this distance as HV, okay. It is just a notation. This book uses L, this book uses HV. So, HV and here you have T by 2. So, the force due to the wind is given by now P is the pressure due to the wind and A is the windage area or the sail area. So, Fv, the force due to the wind, is given by Pv into Av. Now, in general, the expression for wind pressure is So, in general the expression for the wind pressure is half into Cw into rho Vw square, where Vw, this is the wind velocity or the wind speed. Okay, this is the wind speed, and Pv is equal to half. Cw is a constant. It is known as a what constant? It's called as a wind constant, I think. It's a resistance coefficient. It's called a resistance coefficient or wind resistance coefficient. So, so Cw and V is the Vw is the velocity of wind speed. So, half Cw into, it's a constant. Cw has some value, it is 1.2. So, Cw is in general 1.2. Okay. Therefore, you have 1 by 2 into 1.2 into rho is the density of air, it is wind. Okay. So, air is 1 kilogram per meter cube into V. V is the velocity of wind or the speed of wind. It is usually in the range of some probably 5 or 6 meter per second. So, this gives you Pv, the pressure, and Pv when multiplied with A, when it is multiplied with A, that is the wind, the sail area, it gives you the total force due to the wind. Okay. Then so, let us assume that this is the initial water line, and then the ship heels to a new water line. Okay. It heels by an angle phi. Then this distance is Hv, this distance is T by 2. At this point the R acts. R is the reaction force from the water. At this point F acts. This is the reaction force from the wind. This is the force from the wind, and R is the reaction force from water. So, these two forces act. Now, the ship is now heeling. It's like this. Now, as you can see, there is a force like this, there is a force like this. So, it causes it to heel like this. Just like we can imagine, when a wind acts, it will cause it to heel like that. So, this heeling, it causes it to heel, and that is what is shown by W1 L1. It is a new point of heeling. Now, at this point also, if you draw the vertical in this, okay. So, this is the, remember W1 L1 represents the horizontal, that vertical. So, the reaction force from the water is always horizontal, because it will never change. It will be like this, R somewhere here. It won't be exactly in line with this, it will be somewhere up, and there will be an F here, somewhere here there will be an F. Now, this distance, what we are talking about is, if it is like this, okay, initially, then it tilts like this. So, this center is actually moved up a bit, okay, and that point has moved down a bit, and the vertical distance between them at that point is not now equal to Hv plus T by 2. It is slightly different. It is with an angle, that is, it will be this distance. You can just look at this figure, it will be like this. This will be Hv and this will be T by 2. This will be phi, means, or is that phi or is the other one phi? Yeah. Yes, correct. So, no, this is not Hv, this is not T by 2. This is Hv, this is the vertical, no, at that point, Hv, and this is T by 2. Now, the vertical distance at that point between them means when it is tilted like this, this is the vertical distance is now not equal to Hv plus T by 2, it is Hv plus T by 2 cos phi, Hv plus T by 2 cos phi. Okay. Now, note that wind is acting always horizontal. Similarly, that is, the wind is always acting horizontal. The wind does not, even though the ship tilts, the wind does not tilt with it. Therefore, what is the force? Force is pressure into area. Now, pressure into which area? Area is, it is the area that is perpendicular to that direction of force, okay, the direction of wind. So, this velocity of wind is like this. The area that we need is the area that is perpendicular to it. Now, when this area tilts like this, the area that we need is a projection of this area on this plane, okay. Therefore, that also becomes A cos phi. If this area is A, this area itself will be like this. This area in this projection will become A cos phi. This angle is phi. So, A cos phi. So, the area, the windage area reduces to A cos phi. Okay. Now, that you have these two values, I mean you see these two things, let us write what is the expression for the first of all, what is the moment due to the wind initially? Okay, it is initially in an upright condition. What is the moment due to the wind? It is the force in, now this force is the wind force, there is a reaction force, this reaction force will be equal to the wind force, because this is trying to equalize that such that the thing is not, such that the ship is not moving horizontally. So, they are balanced. So, it is this force F, which is the wind force, equal to the reaction force, that force into the distance between them, that is the moment causing the turn. So, the turning moment, so the turning moment is equal to F into distance between them, which is PV AV into HV plus T by 2. Okay. This is the turning moment, and the turning arm on the ship, okay, it is not the turning arm of the wind, it is the turning arm on the ship. I will tell you what is the difference, that is the turning or heeling arm on the ship is this moment, which is PV AV into HV plus T by 2, this moment divided by delta of the ship. Okay, they have put G also, that means delta is in kilograms. Okay. So, you want the force, means you want the arm. So, it is force into distance divided by force. Force is mass into G. So, there is a weight. So, this is delta into G. Okay. You see why I said it is the heeling moment, heeling arm of the ship, that is because you have divided with the weight of the ship. It is not exactly the moment causing the, it is not exactly the arm that causes the moment as far as the force is, means if I divide it by PV AV, you will get a arm, that is a HV plus T by 2. That is not what we are calling by heeling moment. Heeling arm. Heeling arm means the force into distance between which it acts divided by the weight of the ship. The ship is what is being heeled. So, we are talking about the heeling moment of the ship or heeling arm of the ship. Now, the heeling moment of the ship is equal to the heeling moment of the force, because this force is what is causing the moment. So, the heeling moments are the same, but heeling arm of the ship is not the same as the arm that causes the moment of the wind. The arm that causes the moment of the wind is HV plus T by 2, but the heeling arm of the ship itself is HV plus T by 2 into PV AV, that gives you the moment divided by the weight of the ship. That is the heeling arm of the ship. That is usually designated in this book as LV. At 0 angle of heel is this HV plus T by 2 divided by delta G. Okay. This is the expression for the heeling arm of the ship due to wind. Okay. Or you can say heeling arm on the ship due to wind, because heeling actually acts on the ship, whereas righting is a property by the ship, means righting arm is done by the ship to come back to its position, heeling is done on the ship to go to the final position. So, this is LV as a function of this thing. So, now remember in the previously we have said when the ship heels by an angle phi, the healing, this distance changes by hv plus t by 2 cos phi. As directly proportional to this, you can see that LV will also become directly proportional to phi. So, LV at some phi will be PV AV into cos phi. I will tell you, if you want I will explain this again, HV plus T by 2 cos phi divided by delta G. Why did I say this? That is, if you see this original definition, we say that when the ship is heeled now to an angle phi, its windage area becomes A cos phi. So, I have made this A cos phi, this is at an angle phi, its windage area is now A cos phi, it is this, and its vertical distance between the two forces at that instant when it is heeled by an angle phi is hv plus t by 2 into cos phi. Therefore, the vertical distance is hv plus t by 2 into cos phi. Okay. So, this becomes your LV at some angle of phi heeled, means initially when you have initially when the ship is upright, wind acts, a heeling arm on the ship is proportional to hv plus t by 2, this one, this is your heeling arm. When it is heeled by an angle phi, it is now proportional to the initial value into cos square phi into something. You can see one cos phi from here and one cos phi from here. So, it is proportional to cos square phi into these values PV, AV, HV plus T by 2 by delta G. Okay. So, this you have to remember, that is LV becomes proportional to cos square phi. This is one point here. Now, this is as far as the basic physics is there concerned with the wind heeling moment. Now, we will see how the stability criteria regarding the wind heeling is taken to done. It is done for different ships, that is the different IMO criterion, how they make the rules. We will do that. Okay. All right. Now, the way we proceed is like this. These are a series of steps. First, let us write down the steps, and then we will do a problem. By that time you should be able to understand how it is applied. Okay. That is, okay. First of all, you assume that a force of, it is something like this, pressure PV equal to 48.5 kilogram per meter. It is in kilogram. Okay. Those dimensions please note. Usually pressure is, in the previous definition we put pressure as in terms of Newton per meter square, but this is in terms of kilogram per meter square. It does not matter, you have to multiply with the G actually. So, 48.5 kilogram per meter square. So, first you assume that so much of PV, a wind of so much of PV is acting, it acts. Okay. So, a wind with this much of pressure equal to 48.5 acts continuously, it is a steady wind. Now, this produces a force F given by this pressure into windage area. Okay. This will give you the force on the force acting due to the the wind force due to the wind. Then we define a lambda 0 as F into L, where L is your LV, as in the previous definition. This is F into this LV is HV plus T by 2. Okay. Is it clear what is that HV plus T by 2? That is the heeling. This is just the moment due to this whole thing. Lambda 0 represents the moment due to the wind. That is all. The moment due to the wind, which is force into the distance between the two forces. That is the wind force acting here and the reaction from the water force acting here. There is a distance between them, and there is a, because of this two forces acting, there is a moment tending to turn the ship, and that moment is F into L. F is the force and L is the distance between them. That distance is hv plus t by 2. Then we call this as lambda 0. Okay, just note these things. It's termed as lambda 0. Then okay, now I'll just write it step by step. Then now we assume that, actually if you do not follow completely, we will do the problem and then it will become clear. Assume that the ship is now heeled, ship has heeled. Now assume that the ship has heeled by 15 degrees. Okay, that is the next step. You assume that the ship by now has heeled by 15 degrees. Then I will explain again, as I told you. Then you calculate, you have lambda 0, you are calculating a safety, giving it a safety factor of 1.5 lambda 0. This is like saying this 48.5 Newton, you get a wind, by making it 1 point, means you calculate some moment, making it 1.5 lambda 0, the meaning is that you assume the worst case. Okay, that means this is a design criterion, that means we really do not know what is the wind, and in general the wind is maximum is about 48.5, that is why we have chosen that to be 48.5. That is the maximum value, because we are not, we do not care what happens at the minimum case, that is not a problem, only our worst cases we are designing. So again, in addition to that, you assume a safety factor of 1 point, that means you are assuming the moment acting on the ship is now 1.5 lambda 0, not just 1 lambda 0, but 1.5 lambda 0. So that we assume to be 1.5 lambda 0. Then this I will explain, that is, you have to find one area S1 under the GZ theta curve. This is, you have to GZ phi curve, which area is this S1? That is, this is the area under the GZ curve between the writing moment and 1.5 lambda 0. Means, okay, if you do not follow it, we will see what it means. So that is, it is the area under the GZ phi, and this is the writing arm curve or the writing moment curve, and a 1.5 lambda 0 curve. This is the heeling moment curve, heeling arm. Okay, then once you calculate that S1, we assume that you find a theta dynamic which is defined as, that is from the point, to explain this, okay, probably I will do one thing, I will do the problem and in step by step I will explain. At any rate, this you find a theta dynamic where, that is from the point where the ship has heeled, we find an area S2 such that S2 equal to S1. I will tell you what this is, very sounds a little confusing. So, I will write it first, S2 equal to S1, and the final condition is that theta dynamic should be less than the angle of flooding. I will explain how this theta dynamic is found, we will do that problem. So, the criterion is that the theta dynamic that you are getting finally, okay, what exactly are we doing? What we are doing is, we initially have the ship in some condition. Okay. Now, it could be like this, it could be like this, some condition you have the ship initially. Now, you are providing some force to it, you make it tilt to some position. Okay. Now, while it is tilting to the new position, this is the physics behind this whole step. Okay. This you should, if you understand this, then it is easy. So, from the initial state, wind starts acting and this starts tilting. Okay. and it reaches some state. Now, even while it is tilting, it is having a gz, means it is having a righting curve. Now, some energy is imparted from the wind to the ship. The ship does some work in resisting that wind. Okay. Now, that means, so the difference between the two will give you some work or some energy that is given from the wind to the ship. Okay. Now, what happens is that you assume that this whole energy that is given from the wind to the ship causes that ship to tilt further, means without the wind acting now, the ship is now tilting. Okay. With that new found energy, it is heeling further. You find out the maximum angle to which it will heel, and you say that that angle of heel should be less than the angle of flooding. This is the general physics behind the whole process. We will do this problem, and this is that final angle through which it comes is known as the theta dynamic. That means, when I said two areas should be equal, the meaning of that is that area is obviously the energy, right, means I have told you what is the area under the GZ curve. It is dynamic stability. It is the work done by the wind, and when you work done by the wind and work done by the ship. In now, dynamic stability is the work done by the ship, and if you calculate the area under the wind curve, it gives you the work done by the wind. Okay. So, you have two curves in the GZ. You have a GZ curve, you draw sometimes a heeling curve. I have already shown that. So, this area under the GZ curve, I will draw this. Okay, you have a GZ curve like this. Now, the area, if I take the area under this curve up to some degree, let us say 20 degrees, okay, I get the work done in heeling the ship, work done by the ship in righting the ship up to an angle of 20 degrees. That is what this is. Means some heeling moment is acting, the ship is heeling, but it is trying to right itself. Always there is a righting moment. So, the heeling moment minus the righting moment is acting, but it still heeling moment is higher. So, it keeps going. Okay. The work done by the righting moment is given by the area under this curve. Okay. I think it should be clear. Now, on this we draw sometimes a heeling arm. Okay. The area under this curve, let us say this area, up to 20 degrees will give the energy given by the wind into the ship for heeling it. So, the first one is the energy given by the wind to the ship, the other one is the work done by the ship in resisting that, which is like saying that the energy taken out of the ship. One is the energy given into the ship, the other is energy taken out of the ship. So, the difference between the two will give you the net energy given to the ship. Okay. That is the area between, that is what we mean by the difference in area between the heeling arm curve and the righting arm curve. Righting arm curve is the resistance and this is the work given, energy given. So, the difference between the two will give you the energy, net energy that is given to the ship. Okay. So, what happens? So, up to some, initially the wind keeps acting, it keeps giving some energy to the ship, it keeps heeling, then let us say the wind stops, then but still the ship has some energy, because it has more energy because a wind has given it some energy, right. So, it keeps heeling further. That final angle to which it heels is what we are calling as theta dynamic. Now, that should be less than the angle of flooding. Okay. Now, let us do one problem that should explain it. Okay. That is, first of all, the GZ table is given. So, you have the heel and GZ. So, that you have GZ is given, okay, that is given. Then you are given the displacement of the ship, then kg is given, km is given. So, from this you can directly get your gm, okay, there is no problem in calculating gm. Now, you are told that the draft is 11 meter, you are given the windage area is 3,800 meters square, and you are told that the centroid of the windage area is 6 meter above the water line. This is obviously your HV according to our definition. HV is equal to 6 meter above the water line. Then you are told that the angle of flooding is equal to 34 degrees, and one more is required, which is known as the angle of deck edge immersion, and that is also given to be some value 23 degrees. Now, you are asked, is the ship stable, will it pass the stability test? So, this is the whole, we will see the whole test we have to do. Okay, now, first of all we have to find the wind lever. As we have said, it is HV plus T by 2. Okay, this is very straightforward. T by 2, T is the draft, so T by 2 plus HV, everything is given. So, this you can calculate. Then remember, we have to calculate a lambda 0. I have defined that lambda 0 is equal to the moment due to the wind, which is defined as, which we can calculate it as windage area into windage force, wind force, into that distance, or which is the wind lever, divided by the displacement of the ship, divided by wind lever divided by area into force in a wind level. That is the lambda 0 is the moment itself, it is not the arm. So, it is just that. Okay. So, windage area into wind force into lever, and that gives you something. Okay. That gives you your value of lambda 0. Okay. Then now, you need to calculate a 1.5 lambda 0. This is necessary for the calculation. So, you calculate a 1.5 lambda 0. Okay. Then I will draw this. So, first of all, you do in this problem, I think the only way to do this is by graphical method, that is you have to have the graph and you have to draw the figure. So, you draw the GZ curve first. Now, first thing to do is, so this is GZ, and this is GZ, we will put delta into GZ, writing moment. It is not the GZ curve, it is delta into GZ, which is your weight of the ship into GZ displaced. So, this is actually showing the writing moment. Now, the important thing is that is in this moment. So, this is the moment phi curve, not the GZ phi curve. So, it is almost the same thing, it is delta into GZ versus phi curve. In this, we instead of putting the heeling arm, we will obviously put the heeling moment, because this is the moment phi curve. So, first of all, in this you put lambda 0, that is your heeling moment. Okay, lambda 0, you mark that point. Let us say this is lambda 0. You draw a straight line there. First of all, I am just going to go step by step on how this is done. So, lambda 0, you draw a straight line there. Similarly, to lambda 0, you draw a straight line at 1.5 lambda 0. This is 1.5 lambda 0. Now, what we are going to assume is that at lambda 0, so at lambda 0 we assume the ship, that as I told you before, as we are assuming that the ship has heeled 15 degrees into the wind. The reason why we are doing this is, this trial and error kind of thing is because we do not know where the initial position of the ship is. It does not have to be upright, or okay, it does not, we do not know anything about the ship. So, it is in some initial case. So, we are assuming it to be in the worst possible condition. Everything is worst, means maximum wind, worst possible conditions. So, the exact calculations we are not doing it here, but we assume that the worst condition is about like this, means this is 15 degrees. So, the meaning of this is the ship was initially like this, okay. It is not 0, it is not upright, it is at some point like this, and then it is wind acts, and it caused it to be frank, actually that windage area will become a cos phi and all that, but that calculation is, it does not matter, it is not exact calculation we are doing the maximum values and all. So, it is initially at 15 degrees, the wind acts, and then it rotated through 15 degrees. That is the meaning of this term, that is, we assume that the vessel has rolled 15 degrees into the wind. So, from its initial position, as it has assumed 15 degrees into the wind, as a result of which it comes to this position, okay. So, this position we know now, because we know lambda 0, we know the GZ curve. So, we know this position, we go 15 degrees back. So, this was we assume to be the initial position of the ship. So, the ship is initially at this position, it heeled and it came to this position because of the wind acting. Now, just for a purpose, means no, if the wind is acting like this, ship will heel only like this now. Yeah. That becomes a different case, then means it does not matter, you look at it from in this case, okay, let us see, this is a worst possible condition, means let us see, what you are saying is that if the ship is initially like this and the wind acts like this, what will happen? Which is the worst condition, which is the is that the worst condition? Well, actually, will that be the worst condition? Actually, there is an analogy, that is, if you consider a pendulum, okay, if you that is, if you have a pendulum standing, if it is upright like it is hanging upright like this, you give it some force, it will move to some distance, okay, that is all right. Now, if it is like this and you give it the same force, it will move a greater distance, okay. And if it is like this and you give it some force, it will actually move a lesser distance. Actually, do you understand what I am saying? This, when it is here and it is pushed, it actually moves a greater distance, same force than if it is given here. But on the other hand, if it is like this and you give it the same force, it will move less than the same condition. Maybe we can think of it in terms of energy, that gravitational energy also comes to move it. In this case, it is like a gravitational energy, that means here there is some gravitational energy. In this case, there is a change, when it comes like this, there is a change in gravitational energy, right, potential energy I am saying, not gravitational energy, it is a potential energy. So, because that adds to this and it causes it to move further, means it causes it to heel further. On the other hand, if it is like this, it is subtracted, that difference is not there, means it is known, but the exact reason I hope it is correct, that is, you think logically, intuitively, that is, if it is like this and if you push it, will it go further, or if it is like this and push it, will it go further, or if it is like this and you give the same force you are providing, will it go further. The same thing is happening for a ship actually. This is like trying to think which is the worst condition. If it is like this and you give it a force, will it go more, or will it here and give a force, will it go more? It is like, and or if it is here, like you are saying it is like this and you give it a force, will it go more? So, it is the physics says that if it is like this and give a force more, it will go, but to really explain it, I have to think a little more, I think, because I think it has to do with the gravitational energy, potential energy only, that difference, because that much energy is added to the ship when it is heeling. So, to the wind force, this additional energy adds, whereas in this case, to the force, that additional energy is subtracted. So, only that much energy is going to do work against the motion. Okay. So, this is actually the worst case, though it goes little bit against your intuition. This is the worst case, not this. Here it will go a little, but in this case it will just go too much, means from here it will go all the distance here and more than that. See what I am saying? That is how, that is what the physics says. So, this is the worst condition. Okay. So, you assume this to be like this, and force is acting, and then it goes much further than it goes if it is like this. Okay. So, it goes like this, then it tilts, it goes. So, we assume that it has tilted up to 15 degrees. So, from here it has tilted up to this. Now, what we can do is, we are just going to provide a safety factor. There is no logic to it except that it is for safety only. Means you assume there is, if you assume that x is the amount of energy that the wind has given to the ship, let us give it a safety factor, let us assume that 1.5x is given, just that, just to make sure that you are within, means in case there is some other error somewhere, make sure that we have taken care of all that because of this. Because of that, so you make it 1.5x. So, that is the meaning of this. Now, so this becomes this point. Okay, the graph between, so instead of it starting from here, actually it has happened, only this much has happened according to the wind, but we assume that this much has happened and we do our calculations based on that. So, the ship is now here and it is now heeled by this much degrees. Okay. From this 1.5, this is the position of the ship and it has heeled by so much degrees. Okay. Now, what we are assuming is, so the difference in area between this curve and this curve, which is basically this area, this is the difference in area between the two curves, is given to the ship. Okay. So, that much area is given to the ship, means that much energy is given to the ship because of this. The difference in area, I have told you, the difference in area between the writing arm and the heeling arm, or the heeling arm and the writing arm, will give you the difference in energy between the energy given to the ship and the work done by the ship in writing it. That means that much energy it has got, excess energy it has got. Now, what happens? The wind has stopped. Once it has reached this point, we call this, we will call this, I think this is theta 1, we will call this theta 1. Okay. And I think that is what they are called, theta 1. So, if this is theta 1, now from this, so this much energy has gone into the ship. So, what are we assuming? The wind has stopped, but that energy is still with the ship. So, the ship heels further because of that energy, excess energy it has got, the ship is heeling further. So, from here, this within this GZ and it keeps heeling, what happens? Work is done again by the writing moment. Now, wind has stopped. Okay. Wind is not acting, but the ship keeps heeling, writing moment keeps acting, because the writing moment is still trying to produce bring the ship back to its original position, and when the work done by this writing moment becomes equal to that excess energy, what does it become? It stops. So, at that point the ship really stops heeling. Okay. Therefore, what should we do? We should provide an area here which is equal to the area under this area. If you put this area here under the GZ curve, that area will become, it is like saying that that energy that has gone into the ship is now used completely for heeling the ship. That is the thing. So, you keep going till that area is filled up. Okay. The whole area, which is the GZ curve starting from, wherever it is starting from, the whole area, it goes till some value theta dynamic, till this area is equal to this area. So, you reach theta dynamic, and this theta dynamic should be less than some flooding angle. Okay. So, if you want, I can explain this again. It is like this. I think I will do this. This is a little confusing. So, initially you have the you have your GZ curve, So, let us draw first the delta GZ curve, which is the moment into heeling arm, moment into righting arm. So, delta GZ, that is the righting moment curve, this is the righting moment curve. Now, in this righting moment curve, let us draw the heeling moment first. This is lambda 0. We have already said lambda 0, which is a product of the force, wind force, into the distance hv plus t by 2, which is the distance between that two force centers, that is lambda 0. So, you mark lambda 0 here, you draw a straight line. So, it hits here. Is this, what angle is this? This is, sorry, this is theta 1. Okay. So, this is theta 1. Now, at 1.5 lambda 0, you draw another line, this one, 1.5 lambda 0. So, at 1.5 lambda 0, you are drawing another line. This is just a safety factor. Now, at what we are assuming is theta 1, it is now at theta 1. Okay. As he said, there are two ways. Okay, we do not know the initial position of the ship. The ship has actually one more reason for that is this theta 1 is the final position of the ship. Now, it will always occur only in the direction of wind, that heeling must have occurred only in the direction of wind. So, first of all, that itself will tell you this is the only direction in which it could have come. I mean, if the wind is acting like this, then only it can come to this state. Otherwise, it should have been in this state, it does not make sense, there is no such logic. So, it is in this state, let us say heeled this much, it is due to a wind acting continuously like this, that means it is like this, it has started from here, in case means it is heeling in the direction of wind always. So, at lambda 0 it is heeled, we assume that because of this wind it has heeled by a maximum of 15 degrees, that exact reason for the 15 degrees is not necessary, but assume that it has heeled through 15 degrees. Therefore, it has heeled from here, we have to extend this GZ curve. Okay. So, the ship started from here, this was its worst condition and it heeled up to this theta 1. So, from here wind kept blowing and it heeled up to theta 1. We in a way we found theta 1 and then we went back saying that it started 15 degrees before. So, we do not know what is that initial position, that is why they have said assume the ship is in the worst condition, this is the worst condition. Okay. Then, so it started from there and it went up to theta 1. Now, we just give it a safety factor, we make it 1.5 theta 1 just for safety. So, this is 1.5 theta lambda 0, 1.5 lambda 0. So, it is this is your heeling moment is 1.5 lambda 0 and not lambda 0. So, that is the first thing. Then, so once you have that, this is this angle where it hits GZ, this is like your theta 1 that is with a safety factor, theta 1 with a safety factor, that is here. Now, you find the area under this curve, under the GZ righting arm curve, under the righting arm heeling arm curve. Okay, that angle between this is the heeling arm 1.5 lambda 0 and this is the righting arm. So, the area under that curve will give you the net amount of energy that is input into the ship because of the wind. Now, if the wind now if this ship keeps heeling with this energy, it will heel up to an angle of let us say theta dynamic, which means that this area is put here. Okay. This same area should be extended here and therefore, we find the theta dynamic and we say that theta dynamic should be less, these are the two conditions, this I will tell you, that is theta dynamic should be less than the angle of flooding and this theta 1 which I have drawn here, not theta 1 safety factor, theta 1 itself should be less than 0.65 times the angle of deck immersion, deck edge immersion. Okay. Then, so this is your two conditions which should be satisfied by the ship finally. This is what we are going to check finally. If it satisfies both of this, we say that it has passed the test. Okay, now let us do that problem. So this is what we are going to do. Okay, so we have first we calculate the wind lever, we have calculated, then you calculate lambda 0, which we have done, then we do 1.5 lambda 0, then so first what we have to do is, so definitely the first thing you are going to do is draw the GZ curve. Based on the GZ, you are given the GZ table in this case. So from that you draw the GZ curve. So first you will do this lambda 0. You have already calculated lambda 0 and 1.5 lambda 0. So lambda 0 will come here, 1.5 lambda 0 will come here. So 2 lines you are drawing. Now from this point, this is theta 1. Okay. This you read from the table, it comes to some 8, I think 8 degrees. This is just, that is why I said this problem you have to do it in graph only. I do not see any other way of looking at that figure. So you will have to draw the GZ curve, then you put lambda 0, 1.5 lambda 0. So you have got theta 1. So you have got your 8 degrees. Okay. Then you have got your 8 degrees, then so obviously from here 8 plus 7, 15 degrees, so minus 7 degrees, it has started from minus 7 degrees. So we assume that the ship has started heeling from here, it has heeled 15 degrees and it reached 8 degrees. Then we do a 1.5 lambda 0, okay, and let us say that it hits here. Now this we have calculated minus 7 degrees. So what should we do? From here you will see that for this particular problem this becomes about 11 degrees roughly. Okay. So for this 18 degrees, that is this 11 plus this 7, 18 degrees, we have to find the area under this curve, this area we have to find. This area we find, and then starting from here, from this angle, you have to have that area, you have to extend it here. Okay, this further like this you have to extend that area, and you have to find the angle to which you have to go such that this area is S1 is equal to the area here S2. The angle to which you have to go, you have to find that theta dynamic. Now it is not that easy, because note that we know this area S1. Now how can we find the area here? That is actually a trial and error process, there is no other way. That is why such a problem I cannot give in the exam, except for asking you the method. Like theoretical question only I will ask, no problems, it is too difficult. So this S1, it goes to S2, you have to find that area up to theta dynamic. So that they have solved, and you get some theta dynamic, some 27, and so therefore you compare finally with these two checks you have to do. Is theta dynamic, you are given these two things, angle of flooding is given, angle of deck edge immersion is given. So you have your theta 1, which is this, and you have your theta dynamic, which is this. Is theta dynamic less than that? Is theta 1 less than 0.65 times this? So these two checks you make, and in this case it satisfies both the checks, and therefore the ship is stable. Okay. So this is, it is a very elaborate process. Know the method properly, just understand that method properly, but I cannot ask any problem on it. So just learn the method. Okay, that is all. Thank you.